Hello everyone, and welcome to AP Chemistry section 1.6. In our last video, we reviewed electron configurations. We learned about how electrons are weird, and they exist in orbitals and shells and subshells. But have you ever wondered, how do we know? And is there a tool that I can use to map out electron configurations? The answer to that is yes. Yes, there is. And it's called photoelectron spectroscopy. So in this video, we're going to learn about what photoelectron spectroscopy is, how it works, and how to read the data that a photoelectron spectrum gives us. So I hope you're ready. Let's get started. Okay, first, let's talk about what is photoelectron spectroscopy. Photoelectron spectroscopy is a method of determining the arrangement of electrons inside atoms and their binding energies, which is the energy it takes to remove an electron from each particular orbital. We've learned from Coulomb's law that electrons are attracted to the nucleus, and the closer they get to the nucleus, the more energy, more binding energy they have, and the energy is required to remove them. It involves sending ionizing radiation, usually X-rays, at a sample and measuring the energies of the electrons ejected from the sample. We're making use of the law of conservation of energy here. And the way it works is the input energy is known. We're going to shoot a known set of energies at the sample. Then that energy ionizes the sample or atoms in the sample and shoots out electrons. All right. That requires a certain amount of energy, and the electron gets the remainder. So the leftover energy determines how fast the electron will move once ejected, and the difference in energy shows the binding energy of that electron in that orbital. So you might see a setup something like this. This is just a cartoon, but the idea is there. The ionizing radiation comes in, ionizes maybe the top layer of that sample. Electrons get ejected, and then they're detected by some kind of a detector that measures their energies. That gets converted into a graph that'll have some peaks on it. And we'll look at those graphs in just a second. All right. So because electrons live in different energy levels, they require different amounts of energy to be ejected. Electrons closer to the nucleus are harder to eject, and electrons farther away from the nucleus are easier to eject. If only a small amount of energy is left over, the electron will be moving slowly, and we know its binding energy must be high, and the opposite is also true. If a large amount of energy is left over, the electron will be moving fast, and we know its binding energy must be low. And there's our diagram again. We're going to get some graphs out of this, and let's talk about the way they're going to be looking. So note, the axis is often but not always numbered backwards. Like this one, lower numbers over here and higher numbers over here. That may switch. And so you just have to look at your graph to find out which direction it's going. Make sure to find the peak of highest energy. That's the one you want to start with, because that corresponds to the 1s orbital, or the one closest to the nucleus. Label that as the s peak and move left or right from there, depending on what graph you got. The scale is usually logarithmic because we have a large range of values in binding energies. And so there may be breaks in the axis to make things simpler, because it might be like really long, so we chop it up a little bit. Sometimes two separate graphs composing one graph over. I'll show you examples of that as well. Okay. Units are usually megajoules per mole, or sometimes electron volts. Okay. And you're going to get some peaks on there. The height tells you the relative number of electrons at a specific energy level, or in a specific orbital or subshell, like 1s or the 2p's or the 3p's or something like that. All right, and there's our axis again. Now what I want to do, I want to start with the easiest element, hydrogen, and just build up to heavier and heavier elements with more and more electrons, so that you can see the patterns develop in these photoelectron spectra. So let's start with hydrogen. Right? We know that hydrogen has one electron and its configuration is 1s1. So there's only one electron to remove, and so we get one peak for hydrogen at this particular energy, 1.31 megajoules per mole, and that corresponds to one electron. Okay, now compare that to helium. Helium has two electrons. They're both in the 1s orbital, so they're both going to have equal energies needed to remove them. And so we get a peak that is now twice as tall as hydrogen because it's got 2 electrons, not just 1. And it's also been shifted over a little bit to the left. Okay, it's at 2.37 as opposed to 1.31. And that is due to the fact that helium has one more proton in the nucleus, and that holds those electrons tighter, requiring more binding energy. And so we get it shifting to the left. That's a common theme for today. Now, watch the magic happen with lithium. Lithium has 3 electrons. Its configuration is 1s2, 2s1. So what we get is a chart like this, where we've got one peak that is 2 electrons tall. That represents 2 electrons. And then a second peak for those 2s electrons, actually just the one of them. And you'll notice that this peak is half as tall as this peak because it's only got 1 electron in there with that energy. So I've got 1s2, 2s1. I'm starting with the highest energy. That's going to be my 1s. And you can actually build an electron configuration based on looking at a chart like this. Let's go beryllium. 4 electrons. Add one more there. Notice what happens here. 1s2, 2s2. They're both the same height, which means they both have the same number of electrons in those orbitals. Beryllium has 2 orbitals being filled, and that's our graph on that. Notice again that the first peak, the 1s peak, is getting progressively farther left on these graphs because the added protons pull that 1s in tighter. And again, that's a common theme. Here's boron. We add a 5th electron, 1s2, 2s2, 2p1, and you'll see this represents 1s2, 2s2, and again, there's only 1 in the p, so it's half as tall, 2p1. Carbon has 6 electrons, 1s2, 2s2, 2p2. And so all 3 peaks are the same height because they all have 2 electrons in each one of those subshells. Now we're going to add a 7th electron. Notice what happens. We start here at the 1s2. That's now at 39.6 megajoules. And then there's the 2s2. Now we have 2p3. And so this peak now becomes taller than the s's. And sometimes I might have to guess how much taller. Like, is this peak going to be twice as tall or 3 times as tall or something down the line? You'll see that in just a second. Let's do oxygen. 52.6. So 1s2, 2s2, and now we have 2p4. Notice that this peak is now twice as tall as the s. So you kind of have to lock in on that highest energy one. Whatever height that is, that may not be written over here. Whatever height that is represents 2 electrons. And then that's 2, and then you kind of estimate, oh, that's twice as tall, so it must be P4. Here we go with fluorine. Similar, but now it's P5, right? It's gotten a little bit taller. And neon, which fills out the 2p orbitals. And that now is 3 times as tall as the 1s. So I got the 1s, that's 2, and then that must be 2p6 because it's 3 times as tall. Hopefully you're seeing the pattern and the building up of the peaks, which is evidence of the building up of the electrons in those orbitals. Here's sodium, 1s2, 2s2, 2p6. Now I've got the 3s comes next. So you do have to kind of remember the order of filling of your orbitals. But again, don't try to memorize them. If you have your periodic table handy, you can always do that and say, oh, that's the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. So there's sodium. We're going to build up a few more. So we can see the D's. There's magnesium, 1s2, 2s2, 2p6, and then now we have 3s, which is the same height as those, so it's 3s2. All right. I want to show you 2 for aluminum real quick. Now, 13 electrons. Note the 2 charts that are there. And I'll ask you the question. You can pause the video for a second. How are they both similar and how are they different? And if you notice that the peaks are similar except reversed, then congratulations, you noticed it. They have the same peaks, but this one goes from lowest to highest and this one goes from highest to lowest. There's no one right way or the other. You kind of just have to look at it and find it. So here we've added the 3p peak with only 1 electron in it, so it's kind of a short guy. Silicon adds another one in the 3p orbitals, so now it's the same height as all the s's. Phosphorus has 3 in the p orbitals. I'm going fast, you can always pause the video. 3, so now it's again 2, 2, 6, 2, and 3. And sulfur. Notice this one now is twice as tall as the s's, kind of like oxygen. And so we end up with 3p4. And chlorine, 3p5. So it's in the third row, p block, fifth column, so 3p5. And we're almost at argon, which, just like neon, will have finished off the p orbitals. And so we have a p6 peak over here, the same height as the 2p6 we saw earlier for neon. A couple more. Potassium now adds the 4s, but it's only half as tall as these guys, so 4s1. Calcium adds the 4s2, so now it's twice as tall, or same size as the other s's, sorry about that. And finally, let's talk about scandium. So scandium, take a look at what happens here. 1s2, 2s2, 2p6, 3s2, 3p6. Here's the 4s2. Notice it's the same height as that. The 3ds actually get tucked in at a slightly lower energy than the 4s's. The 4s's get filled first because they're a higher principal quantum number. But the 3ds, you'll actually see the 3d peak just a hair under the 4s's along there. And notice there's only one because scandium only has one in the Ds. Again, please note that these values for each of these peaks, like the 1s is now way down at 433 megajoules. That's a lot because there's a lot of protons in the nucleus they have to overcome. All right, show you a couple of the other examples. Here's the photoelectron spectra of boron and fluorine sort of superimposed on each other. Fluorine is in pink, boron is in this dark color. Why are the peaks for fluorine to the left of the peaks for boron? Again, it has to do with, they're filling up the same 1s orbital, but fluorine has 9 protons and boron only has 5. And so they're held tighter, and so it's a higher and farther to the left. Now you might also see data in tabular form. So take a look. Here we have the megajoules per mole for each of the peaks in these first 20 elements, starting with hydrogen, and we saw it at 1.31, 2.37, and so on. Note that with added nuclear charge, the ionization energy of a particular orbital, these are all the 1s2s, increases because you got more protons in the nucleus. Here's the 2s. Each column represents an orbital, 2p, 3s, 3p, and 4s down there. The 1s orbital always has the highest ionization energy. So on a graph, it may be on the right, left or right. Take the time to find it because that's your starting point to building an electron configuration. Now, I also wanted to show you this one, which at first kind of looks like two different graphs. But sometimes, because of that logarithmic scale, they'll separate them. And you'll see way up here at 52.6, there's one peak representing 2, and then a second peak here and a second peak there. Notice that the lower numbers down here are at the left, so we're kind of building toward the left. 1s2, 2s2, 2p, 4, so that would be oxygen in that situation. And here's another example of a graph that's split into two parts. Again, scan it over, find the peak with the highest energy. Here it is at 151. That's my 1s2. Then we'll go 2s2, 2p6. Notice this one is actually labeled how many? 3s2, 3p1, because that's half as tall as the 2 that is there. So that would be aluminum on that one. And now let's take a look at a few questions involving photoelectron spectra. We'll include a couple of pause the video moments as well, so feel free to pause them when we get there. And we'll start with this one. A mysterious element was analyzed by photoelectron spectroscopy, PES, and mass spectrometry, MS. Now, I took the mass spectrometry out of this one because we covered that in a previous video. So identify the mysterious element from the spectral data, and we'll do letter C, explain how the PES supports your identification. So this would be like a free response question. where you have to sort of come up with your justification as to what's going on. So first, let's identify the element. I always said find the highest energy peak, which is 273. This one is actually split into 3 segments. This is all one graph, so you again just kind of get used to that. That's our highest energy peak. That's going to be our 1s. So we've got 1s2, and we move beyond that, so we know that that's 2 electrons. 2s2, 2p6, 3s2, and now we're at the next one, which is 3p. And I have to sort of judge how tall this one is relative to this one. This one represents 2 electrons, and this one's just a little more than 2 times as tall, so I'm going to say this is going to be a p5. The element that ends in 3p5 is chlorine with 17 electrons. And explaining how that supports it, you could say it has 5 subshells, 1s, 2s, 2p, 3s, and 3p, and that the 3p is 2.5 times as tall as the 3s, which indicates 5 electrons, and that would make it chlorine. So that's how I would do that. Now, the next 4 questions involve the same 2 photoelectron spectra. So here we go. We've got 2 elements listed below. The units of energy are megajoules, as most of the time. How many shells or energy levels are occupied in element A? And we would look at element A, which is here, and say we got 1, 2, 3, 4, 5, 6. 6 shells being occupied, and so I would choose letter D as 6. All right. Now we could take a minute and identify these elements as well. 6 subshells ending in this one. Now we've gone to 3s2, 3p6, 4s1 is this one. And that would indicate that that was probably potassium. And then we have 1s2, nothing here, 2s2, 2p6, 3s1. So we got 4s1 and 3s1. This one happens to be potassium. This one happens to be sodium. So we can use that information to answer the next 3 questions as well. All right, next question. Which electron is in the valence shell of element A? Now remember, the valence electrons are the elements in the outermost s and p orbitals, not the core electrons down here. So we're looking at outermost s. We've started an s. We don't have an outermost p anymore because this one is now a core electron. We've started the next energy level. So which electron is in the valence shell of element A? That's this one. And so I would choose 0.42 as my choice right there. This one is going to be a pause the video moment to see if you've been paying attention in this video. Same 2 elements, potassium and sodium. Propose a reason why the peak of the highest energy for element A has a higher energy, 347 megajoules, than the peak of the highest energy in element B at 104. Take a moment, pause the video, and see if you can correctly answer that question. All right, and if you chose letter B, congratulations, you were paying attention in this video. They are higher because they are closer to the nucleus. Potassium has 19 protons pulling them in closer. Sodium only has 11 protons pulling them in, and so it's held less tightly in sodium. All right, and the last question. Which element would be more reactive with water? Element A or element B, based on those choices. Now, we're supposed to sort of understand that, yes, this is potassium and this is sodium, and judging by our experience, we know that they're alkali metals, and they react with water, but not in quite the same way. One is a little more vigorous than the other one, and it turns out because this has a lower energy than this one, it's held less tightly and is more easily lost, which indicates more reactive. So the more easily the electron is lost, the more reactive the element is. So we're going to say element A is more reactive because the least attracted electron is 0.42 megajoules. Okay, then 2 more quick questions. They're similar to each other, so if you can follow along the first one, you should be able to do the second one. Here we have not a graph, but a data table. Same data, just presented differently. The photoelectron data for sodium, which we just saw, is shown above. Which of the following statements is true about this data? Are all 11 electrons shown in the table? Let's check. 2 plus 2 plus 6 plus 1. Yes, they're all in there. Great. There are 9 valence electrons. Now, I'm immediately going to go with the red flag on that one because I know that the maximum number of valence electrons is 8. 2 from the S, 6 from the P, 8 is the max, and that's going to be incorrect. Now I'm just going to double check the other answers. The 2s electrons have binding energies of 104. So 1s, 2s. The 2s is actually 6.84. So that doesn't work. That's going to be false. And peaks with the lowest energies are due to the electrons closest to the nucleus. That's also false because they would be the highest energy closest to the nucleus. And so it is true that all 11 electrons are shown in the table, and that's the choice we want to take. Okay, finally, here's our last pause the video moment. Here, you're going to see data for aluminum. And take a moment, pause the video, and see if you can guess which one of those is not true about the data. All right, when I looked at this one, I chose letter C as not true. The p electrons are all at the same energy of 7.19. Now, this is 1s2, 2s2, 2p6. All right, so those are all at the same energy, but there's actually one more p electron up there, and that's an electron that's at 0.48, not the 7.19. So this kind of saying that all the p electrons are there. And I also didn't like choice D either. It takes 0.58 megajoules to remove a valence electron. There's actually 3 valence electrons, one of them there and one of them there, but it does take 0.58 to remove at least one of them. So that would be, I went with C on that as being the one that is not true. Well, I hope you found this helpful, reviewing a bunch of photoelectron spectra, and I hope it made sense. If you have questions, you can send them to me in the comments. But in the meantime, happy studying and have a great day.